Hi, my name is Amy. I'm the head mathematics tutor at Pinnacle Coaching. So this is part 2 of the series of videos on geometric application of calculus, specifically applied to maximisation and minimisation problems. So for those of you who haven't seen part 1 yet, I left the link down in the description box. You want to watch that before you watch this part, or it's not going to make a lot of sense for you. So let's get started. Alright, so as I mentioned in the first part, there are typical types of questions that gets examined in this maximisation, minimisation area. So in the previous part, we've looked at the application to a volume question. And in this one, we're going to take a look at how it applies to speed, distance, time relationship. Alright, so let's have a look at the question and see how we approach something like this. So in the diagram, it shows a straight section of a river, 1 kilometer wide, blah, 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 blah. I'm just actually going to show you the diagram and just run into what exactly is this describing here. So this is the river, okay? It's 1 kilometer wide, meaning that is 1 kilometer, okay? And what you're trying to do here is you're going to row across and then you're going to jog. What you're trying to do is get from point O to point B, and you want to get there in the shortest time possible. That's pretty much the gist of the question. And if you read the question, we have Phelps here who can row at 6 kilometers per hour, so that's the speed of rowing. And he can jog at 10 kilometers per hour. So that's all we know so far. Let's take a look at the question itself. Alright, so what we are trying to do in this question, if you sort of go to the second part, is trying to minimize the time it takes to complete the journey. So if you remember, we're trying to row across the river and then jog along the bank. So in the first part, we are going to establish an equation for the time. So time, it takes for Phelps to reach from point O to B is this expression here. So let's see how we do that. Okay, so we're now going to try to build the expression for the time it takes for Mr. Phelps to row across and jog along to get from point O to point B. So analyzing the diagram first, we've got speeds. We are trying to get an expression for time. So we need to start by actually having some clarity around between speed, distance and time, so we know what we are building. So right at the beginning, I've mentioned speed is equals to distance on time. Since we are trying to build an expression for time, if you sort of rearrange that, just multiplying that across, so sort of cross multiplying here. Another way of looking at the relationship is that time is equals to distance on speed. So in other words, we need to know what is the distance and what is the speed for each segment before we can build an expression for time. So have a look at the equation here. We've got x is here, this is 1, and this whole length AB is 2 kilometers. Picking on the obvious, you've got a right angle triangle here, so Pythagoras will give you OP, which would be square root of 1 squared plus x squared, just basic Pythagoras. And PB will simply be 2 minus x. That's it. Okay, so now that we've got the relationship, let's have a look at the time for each of the segments. So the time it takes to do the rowing. Okay, so to row from O to P will be the distance, which is the square root of 1 plus x squared, on the speed it takes to row, so 6. On this section, the time it takes to do PB, to jog, will be the distance on the speed. And that's it. So therefore, the total time will be the two added together, which gives us this expression. So now that we've established the expression, we are now going to show that if Mr. Phelps wants to minimize the time taken, he has to row to a point P that is 3/4 kilometers from A. So it's a minimization problem. So let's take a look how we do that. Alright, so now we're going to try to find the minimum that is going to enable Mr. Phelps to get to point B in the minimum time possible. So let's start with the time equation here. I'm just going to do some basic fixing to make it a little bit easier to differentiate. And turning what that square root into power of a half. Same with this one, I'll just leave the 1/10 out like that. Okay, and just differentiate. Alright, so let's differentiate this. So we differentiate t with respect to x. I think it's much cleaner in this expression. It's mostly numbers, and x is clearly a polynomial. Alright, so 1/6 is just a constant, leave it alone. Chain rule on the differentiation. Bring the power down. Subtract the power by 1. Multiply by the derivative of the inside, plus 1/10. The derivative of 2 is just 0. The derivative of minus x is minus 1. So just cleaning that up, I'm just going to cancel out the stuff. So we get 1/6 x on square root 1 plus x squared minus 1/10. Okay, or I'll just clean it up even further, you get this. So once we found the derivative, what do we do next? We are looking for the stationary point essentially. So we're going to solve this to 0. Move the 1/10 to the right side. Cross multiply. Square both sides so we can get rid of the root. And then expand the right side. And then I'm going to make x the subject. I'm going to move the 36 across first. Divide the 64 across. Square root that. So it's going to be plus or minus 3/4. I mean, the question tells you it's going to be 3/4. Good idea to explain why it's a positive and not a negative, because it's a distance. So it has to be positive. So therefore, x is equals to 3/4 only. Okay, so now we need to show that x is equals to 3/4, it is in fact going to be a minimum. So how we're going to do that is, instead of differentiating that, again that's very complicated, just look at the first derivative table. So we're testing around 3/4. So you might want to test 0 and 1. Sub these guys into the derivative itself, you get negative 1/10 and 0.017. So negative. Stationary, positive. Therefore, it's going to be a minimum at x is equals to 3/4 kilometer. And that is it. Alright, so now we're going to take a look at the third part, which is an example of a very tricky question in a maximisation minimization problem. So Phelps decided he doesn't want to row anymore. He can swim faster than he rows. So he can row at 9.5 kilometers per hour and jog at 10 kilometers per hour. And we need to reconfigure the equation and see if anything changes. Let's take a look at how to do that. Alright, so let's take a look at the effect of Phelps' decision to swim instead of row. So this is our previous equation. So you can see the time equation, if he decides to just row and jog, is on 6 and on 10. Now the major difference is the speed. If he decides to swim, he can swim faster at 9.5 kilometers per hour. So it basically replaces the 6 with 9.5, doesn't affect his jogging speed. So I've gone ahead and done the basic calculus work, so I haven't shown all the steps. It's very similar to how you would differentiate the original equation, but I just want to show you the difference in the result. So if you differentiation, that would be the derivative, solve it to 0, make x the subject. The key point is you get 3.04 kilometers per hour. Okay, I mean you can pretty much ignore the negative because it's a distance, it shouldn't be negative. Alright, so what is wrong with 3.04? Come back to the diagram. Okay, take a look. Take a look at the diagram right now. See if you can pick up what's wrong with 3.04. Can't see it? Let me show you. So, if you look at the distance from A to B, it's only 2 kilometers. So what is the 3.04 supposed to be? It's supposed to be the value of x. It's saying x is longer than the actual length you have to travel across. So you've gone outside the natural domain of this particular equation. Now usually when that happens, this is where you have to study the endpoints of the domain. So the global maximum or the global minimum in this particular case is not actually a turning point. And that's in the endpoints of the domain. So how do you know where are the endpoints of the domain? Very easy. You just think about the smallest x could be and the biggest x could be. So the smallest x could be is if it's basically x is 0, so you're literally going that way, swimming right across and then just jogging along the bank like that. Okay, so that's when x is equals to 0. The other possibility is when x is equals to 2. And how would that work? You literally will be swimming directly across to B. Okay, so if you sub x equals 0 into the new time equation and just have a look. Okay, so for x equals 0, you get 0.3 hours. And on x equals to 2, same thing, let's sub it in. You can just use your calculator to work that out. Okay, you get 0.24 hours. So it's just a matter of observing which one is the smaller value. Obviously, this one is a smaller value. So that's your global minimum. Meaning, to answer the question, if he changed from rowing to swimming, he can minimize the time it takes for him to get across to point B by simply just swimming all the way. So basically the conclusion here is if Phelps decides to swim, he's actually much faster just swimming directly across, and that's going to be our minimum time. And that's the answer to the question. So this type of question in typical exam questions, they don't appear very often, but if they do appear and your answers don't seem to make sense, check the endpoints of the domain. I hope you found this video helpful. Please like, comment and subscribe. And if there are any other topics you would like me to do a video for, just leave it in the comments down below. Thank you for watching.